So the question then is, if I give you a tube and you've already told me there's a polymerase in it, but I say I don't want you to give this back to me until you've figured out what kind of DNA polymerase, one of the things you'd like to know is how processive it is. So how do we do that? So this is a little bit more challenging assay. Hopefully everything we've done up until now is straightforward. Okay? The way we assay this is something called a template challenge assay. Okay, the first thing you do in this assay is you make 2 primer template junctions. One is labeled on the primer, and one is not labeled, okay, at any place. Okay, and I'm going to call this one P star TJ, and the other one just PTJ. Okay, so we need these 2 different primer template junctions, and you'll see why in a moment. So we're going to take the first of these, the labeled primer template junction, and we're going to add 2 times excess of DNA polymerase over primer template junction star. Okay? So if we have 2 picomoles of primer template junction star, we're going to add 4 picomoles of polymerase. Okay? This is going to be in the right buffer and everything else that we need to do the reaction. We're then going to take that material and we're going to add unlabeled DNTPs to start the reaction, plus 1000x of unlabeled primer template junction. Okay? So now we have the polymerase is all bound. All the labeled primer template junction is bound with polymerase, DNA polymerase, because we've added an excess of that. And then we're going to add the DNTPs and a lot of unlabeled primer template junctions. Okay? We're going to then allow the reaction to proceed long enough to synthesize the full template. Or I should say the full-length product. In our example, this would be to synthesize 5,000 base pairs after a single binding event. Okay? If we have our super fast DNA polymerase that we talked about before that goes 1,000 base pairs per second, this reaction just has to go for about 5 seconds, right? Typically, enzymes don't work exactly that efficiently, and so we'd probably give this maybe 30 seconds to do the reaction, okay? Then we stop the reaction and separate the products on a denaturing gel. Okay, so what are they going to look like? And I'm not going to show the ethidium bromide this time because it's messy, but I'll show you. These are the labeled products. Okay, and we're going to have the DNA polymerase will either be none, which will be easy to identify, a high processivity, or a low processivity. Okay? Now, if we have nothing, we're going to get no signal. If we have a high processivity, if this is where 5,000 bases runs, we're basically going to get a band at 5,000 base pairs. So if you have one of our fancy 50,000 base pair or more processivity enzymes, we're going to synthesize the entire product. If we have a low processivity enzyme, we might see things that were, if this is 25 base pair, we might see something that's in the 40 to 45 base pair range. Okay, so we might see a smear of products down here. So the question is, how come we see these? What is it about this reaction that says that we're only looking at what binds, what happens after the first binding event? Anybody want to take a swing at it? Actually, we're running out of time. I'm just going to tell you. Okay? So if you think about what happens, we start with all the labeled primer template junctions bound to polymerase. We add the nucleotide to start that reaction, but at the very same time, we add a 1,000-fold excess of what to the polymerase is exactly the same primer template junction. It cannot tell that there's a fluorescent or radioactive molecule associated with the different templates. So it starts synthesizing, and then according with its properties, it will fall off at some rate. Okay? If it's a super processive enzyme, it may never fall off until it reaches the end of the template. But if, let's just say we're talking about this guy. Okay? Its processivity is 20 to 25 base pairs. At that point, it falls off the template. It has to take 1 second to go find a new template. Okay? Once it falls off, it's not just going to rebind to the same template. There's just as likely it's going to bind to any other template. What are the odds it rebinds a radioactive template? Right? It's 1 in 1,000. So on average, it will bind to an unlabeled template. It can merrily go on and synthesize lots more DNA on those unbound templates, but will we see that in our analysis? No. All we see is when it's bound to the first template. Anything that was going to happen upon rebinding to the labeled template will have 1/1000th the signal that it would have if that were the only template there, which essentially makes it 0. Okay? So by adding all this challenge template, and that's why it's called the template challenge assay, we only measure the first binding event and the synthesis that occurs there. Once it falls off, it goes off into the netherlands of unlabeled templates, and we don't pay any attention to it. So this very rapidly, very easily gives us a way of measuring the processivity of a DNA polymerase. Okay, any questions about that?
Oh, will you label TTJ on your negative?
Oh, you're right. Yes, sorry, I forgot something. On the negative, the primer will be here, right? Not extended at all, because it's labeled. Thanks, Teresa.